So substitution is one method for solving a system of two linear equations. And it happens to be a really convenient choice for this system because one of our equations in this system already has isolated one of the variables. We've got x by itself in that first equation. And if you think for a moment about what that first equation means, the first equation says x equals 2y plus 14, which means whatever this point of intersection is going to be a place where the value of x and the value of 2y plus 14 are the same as one another. But what that means, what that tells us, is that anywhere we see an x, if we happen to be talking about that point of intersection at which x is equal to 2y plus 14, I can replace the value of x with twice the value of y plus 14. What does that look like? Well, it looks like taking that second equation, negative 4x plus 5y equals negative 41, and replacing the x in that equation with the expression 2y plus 14. So what you end up with once you've made that substitution that gives this method its name is you end up with an equation that no longer has an x in it. And when we talk more about solving systems of linear equations and strategies for systems of linear equations in our next office hour meeting, all of the different techniques that we'll learn for solving systems have that feature in common. What we're trying to do is to take equations that have two different variables in them and do something so that one of those equations no longer has two different variables in it, so that one of those equations is a single variable equation. Because as soon as we get a single variable equation, we know what to do with it in order to solve for that one remaining variable. If I want to solve this equation for y, for example, then I should probably distribute this negative 4 and get negative 8y plus negative 4 times 14, that's negative 56, plus 5y equals negative 41. I can solve this equation by combining the pair of like terms, negative 8y plus 5y that I have on the left-hand side here to give me negative 3y. I can also add 56 to both sides to give me now the equation negative 3y is equal to 15. And then finally, just dividing both sides by negative 3, I will find a value for my y variable. Y equals negative 5. But that's not the end of the story, because we only found one of the coordinates for this mysterious point that we're looking for. We found the y coordinate, but we still don't know the x coordinate. And so the last step in any solution of a linear system of equations problem is to take the one coordinate which you just found, plug it back into one of the original equations, or one of the intermediate equations if you prefer, and use that plugging in to find the other value. So if we know that x is equal to 2y plus 14, then now that we know that in our intersection point y is equal to negative 5, we can find out that x is 2 times negative 5 plus 14. Simplifying that out, I get, what, 14 minus 10, that's 4. So my diagram is a little bit misleading. What I suppose I should do is just try and make this look a little bit more reasonable by moving my axes over. There we go. So the point of intersection of these two lines, or the solution of this linear system of equations, is xy equals 4 comma negative 5. And to use substitution to do that, all we did was take that first equation, which is telling us that x and 2y plus 14 are the same at our intersection point, and substituted the 2y plus 14 into the second equation in place of the x. That has the effect of getting rid of our x and letting us solve for y, which is awesome. One quick word of caution about this technique is that whenever you substitute, there's a chance to forget parentheses. So that's a chance you'll have to remember to avoid. Anytime you substitute a value for a variable or a value for an expression for a variable, always hug it with a set of parentheses. Otherwise, we would likely have ended up missing this distributive property step that we did here and we solved for y. So whenever you substitute, remember that set of parentheses. If you always remember it, you'll never go wrong.